So again, so how do you visualize this? How does a piece of cardboard, a flat, rectangle, become a box with an open top in the first place? So you can visualize this, if you just follow along what I've got here. So the length, what does it say we're supposed to do here? So 16 by 30. So let's make it 16. Well, let's make the length 30, I guess. And the width will be 16. Okay, so let's zoom out a bit. Okay, so there's our piece of paper, right? So how do we take this piece of paper and make it into a box? So what you want to do here is you want to cut out the corners. Okay, you see what I've done? Chopped a square out of all four corners of the piece of paper. And what that's going to enable me to do now is fold the sides up to create a box. Okay, so the box does not have a top because we fold up four walls, but we never actually made a top. So like when I'm drawing it here, when it completes and draws a prism like this, there's no top. Just remember that. Let's fold it back down. Now, let's just think about this for a sec. If I cut a really, really, really small square out of the corner of the paper and then fold up the box, it creates a very, very wide and long, but not very tall box. And you can see that its volume is 200 units. If I go ahead and change the height, right, my box seems to grow until around this neighborhood, around 725, and then it starts to drop again, right? So it's like it's rising, rising, rising. It's getting better, and then it's getting worse all of a sudden, right? Because now my box is like too tall and it's not wide enough anymore to be efficient. So again, let's unfold it. And you can see that if I cut out squares that are that big, I've gone too far. If I cut out squares that are that small, I haven't cut enough. So somewhere in here, it looks like around 3.5 or something like that, 3.4 or somewhere. There's a perfect cut you can make that when you fold the pieces up, you create this ideal box that has as much volume as you can create with the constraint that you were given. So again, let's go back and apply our technique to this question. Number one, we are going to ask the question, what is being optimized? In this case, what is being optimized is volume. Now, volume of a box, volume equals length times width times height. Okay? Number two, what is the constraint? Now, the constraint here is we actually need to figure out a way to express both length and width in terms of height. So all we know is that the box's original dimensions are 16 by 30. That's all we've got. We've got to somehow think about our volume equation, right? So then what we need to do is create a function that of the optimized quantity with one variable. Quantity, one variable. Now, again, this is not that obvious how to do that, but let's go back to my picture for a second, see if we can reason this through. Let's unfold the box again because we don't need it to be. Now think about this box's dimensions for a sec. Let's get rid of the 3D picture and we can just look at the 2D picture. Now okay, that let's use a segment. You know that from here all the way to here, right, has to be 30. Because that's how much paper you have to work with in the beginning, from one extreme edge to the other. You also know that the sort of vertical dimension on this in this 2D space, you know from here to here has to be equal to 16. Okay, so now what you need to do is you need to think about, like, okay, if that's true, how far is it from here to here, right? These two sections where this is the actual, let's just make this a bit bigger. I thought that would work. Right? This line that I'm looking at right here, what is the length of this line? Because this, right, when I fold up my box, is the length of my box. You see? When you cut off like those four walls on the side, right? Another way you can think about this, you think about the four walls on the side, then the white rectangle on this page is the base of the box, right? And the base of the box is its length and its width. So its length, we know, is 30, which is the original sheet's length, subtract whatever I cut from this side, and subtract whatever I cut from this side. So we could write down here 30 minus 2x. Right? This like line over here is 30 minus 2x. The same logic, this is 16 minus 2x, right? And once again, once I've folded up my box, 30 minus 2x is the length of the base, and 16 minus 2x is the width of the base. Now all I need to do is think about what's the height of my box. Now again, if you go back to the 3D view for a sec, right? How tall is this box going to be? Well, this box is going to be exactly as tall as whatever the square you cut, right? If you cut a square that's height 3, for instance, like I've done right here, and then what I'm going to do is let's draw a segment from 0, 0, 0 to 0, 0, 3. Okay, you can see that, like, my height, the box I've drawn, is exactly 3 units tall because that's the size of the square I cut. So once you understand this, you realize that, like, okay, the height of the box, let's say, is h. The length of the box is 30 minus 2h, right? And the width of the box is 16 minus 2h. Now, once you have this, you realize that the volume equation can be written in terms of h quite easily. 30 minus 2h, 16 minus 2h, and h. And that, right, this equation right here is going to be the volume that we are trying to optimize. Now, before we go any further with this, let's quickly state its domain. Now, of course, 0 would be the lowest number that makes any sense. If you can't make a negative height, you can't cut a negative square out of the side of this box. What's the biggest square I could cut out of this box? Again, let's ditch the 3D view for a second, unfold the box for a second. Now, if you think about how to cut this box, you should see that once I cut 8, it doesn't exist anymore. Because once I've cut 8, look at my side wall over here and my side wall over here. Once I've cut 8, there is no wall left, right? So it's like I've removed the width dimension completely. So the height you can use here is anywhere between 0 and 8. And again, to just quickly look at our 3D graphics quickly, if I cut, let's fold it back up into a box. If I cut 0, I have no box. I just have a flat surface. If I cut 8, right, I have no box. I just have a flat surface. So you can't, you can only cut between 0 and 8. And again, obviously, if you cut 0 or you cut 8, you're going to get a volume of 0. So v of 0 is 0. V of 8 is 0. So our only choice here is to look for v of some critical point. And it must be a maximum because the two other options are 0. Of course, we're not sure we're going to get one critical point. We might get more than one, but let's find out. Okay, so let's go ahead and do that now. So once we have the function we need, so let's just quickly look at it again. So v of h is equal to, let's go ahead and expand it. So 30 times 16 is 480. Then we have minus 60h minus 32h plus 4h squared. And all of this is times another h, so v of h is going to be 4h cubed minus 92h squared plus 480h, right? That's going to be our volume equation. Again, we can just quickly, let's just go back to this sheet for a second. We'll just confirm all that. So remember I said, let's let h of x be just regular x. W of x is going to be 16 minus 2x. L of x is going to be 30 minus 2x. And then the volume function is going to be h times w times L, right? And then let's just expand that volume function quickly, make sure I did the arithmetic right. So 4x cubed, take away 92x squared, plus 480x, which is the same thing we have here. Once you have this equation, you're ready to go ahead and find its derivative. So the derivative here is 12h squared minus 184h plus 480. That's a quadratic. We know that this quadratic can be, can be solved. So let's go ahead. V prime h equals 0. I'm gonna go ahead and assume this is not factorable. Although I think if we take 184, prime factors of 184, get 2, so we can divide everything by 4. So let's say, so 0 equals 12h squared minus 184h plus 480. Let's make it a bit simpler. Let's divide all items by, all terms, by 4. We're going to get 0 equals 3h squared minus, let's see, 46h plus 120, right? I don't think you can go any further than that, because 3 doesn't go into 46. Okay, so we're looking for the solutions to that equation. I'm going to trust that you can take it from there, but let's just quickly, use GeoGebra to do this. So I'm going to go back to my derivative of f. So I get that. I'm going to go roots, f prime. I'm looking for the two roots. It says there's a root at 12 and a root at 3.33. So I guess it was factorable. I guess we could have looked further into that since it came up with nice numbers. Okay, let's hide a couple things here. Let's hide all of that. So the derivative, okay, is in red. You can see it has a root at 3.33 and a root at 12. The original function, which is the volume that we're looking at, remember, the volume has a maximum here at 3.33 and a minimum here at 12. Let's go back to our question. Our domain is between 0 and 8. So let's write v prime h is equal to 3.33333 or 12. Now, h equals 12, we are going to reject, right? Because this is outside the domain. It's outside the domain because we already stated the domain earlier. The domain was only between 0 and 8, so we're not interested in the answer of 12. Therefore, h, yikes. H prime of 3.333 equals 0. Therefore, h of 3.333 is what we're looking at. So h of 3. Okay, if we actually sub in that into our original equation, all right, that's going to tell us what our best possible volume is. So 3.333, remember, is 10 over 3. It's a little easier to put it in like that, and get the best possible value. So 10 over 3, we'll go back to this. F of 10 over 3 is 725.93. If we graph that point, you'll see that that point is indeed the optimized, best possible volume that you can create. You cannot make a volume higher than 725.93. So equals 93. And then we're going to write the maximum possible volume is 725.93 centimeters cubed. Okay, let's go back and make sure we answer the question. The question says, find the dimensions that will give the box the largest volume, which means its dimensions, right? We should write its dimensions. Its dimensions are h equals 10 over 3. That one we knew. W is 16 minus 2 times 10 over 3, right? Which, let's just sub in quickly. W of x of c. So we get 9.33, or 28 over 3. And the length, we said, was 30 minus 2 times 10 over 3, which would be, let's see, 90 over 3 minus 70 over 3 would be the length. So length is L of 10 over 3 is 70 over 3. Yeah, okay. Okay, so 70 over 3 is the correct length, 28 over 3 is the correct width, and 10 over 3 is the correct height. And those three things combine to create the best possible volume. Let's just quickly go back here one more time, and we'll do the same thing we did before, where we'll go back to H here, hide the 3D view for a second, and let's just graph. So let's create a point that is defined as H, and then our function. So actually, I think I have the volume here, sorry. The volume is, sorry, every time I hit spacebar it animates, and it's just... Okay, which one of these is the volume? This thing, I think. Oh, I see, I drew it as all polygons. Okay, well the volume's, sorry, it's coming from here, so... Okay, so we just use the equation. Okay, so let's just create this quickly. So volume, we said it was equal to H times 30 minus 2H times 16 minus 2H. And what I want to do here is I want to create a point. So we're going to say H and then that quantity, and let's divide it by 50 so it's not so hard to see. Okay, again, if I trace this thing, you can see that the volume, right, let's just quickly watch the volume, right? It is rising, rising, rising as we make H bigger, and then it starts to fall as soon as we get onto the other side of 3.33, right? And that, again, is where our box is getting, you know, less and less efficient versus more efficient. So one last time, this box, right, the volume you can see there makes its ideal point right at 3 point. So let's make H equal 10 over 3. And there you can see I'm right at the ideal spot. That's the best box you can make. Okay, one last question here to do. Two ones. So it says there's a pop can in the shape of a cylinder and then an open top metal can. Now that one I've got on a different file, but let's do the pop can one here. So it says pop can in the shape of a cylinder is to have a capacity of 250 if the diameter of the can is no less than 4 centimeters and no greater than 8. Find the dimensions of the can that will use the least amount of material, include the top and bottom. Alright, so to do this, okay, what we're going to be doing is we are going to be looking at just reviewing some information about pop can. Pop can, of course, is a cylinder. So let's write first down. What are we optimizing? We are optimizing the surface area because we're trying to use the least amount of material. So it's as in, what's the smallest amount of a flat aluminum sheet that I would need to create a pop can that has this specific volume? Okay, what is the constraint? Constraint V equals 250. Now let's write down what we know about a cylinder. So the surface area of a cylinder is 2, okay, times pi, 2 pi r squared Okay, this would think about what this is. This is the top of the cylinder and the bottom of the cylinder. Now the other thing we need for a cylinder is the wrapping, the wall, so to speak. The wall, okay, has a height, whatever the height is, and then it has a width. Now, picture the top of the can and find its circumference. Then unwrap the can into a sheet again, and you'll see that the width of this of the can's flat section is 2 pi r, because that is the circumference of the circle. There's a pretty good demonstration of this in the next question. I think that's probably where I'm going to leave it. I want you to think this through and try and visualize this. Like, why would the surface area be this equation? Like, what are the parts and why do they make sense? But I want you to think that through. Now, the volume is a bit easier. It's just the area of the bottom, which is pi r squared times the height, because it's the area of the bottom just times its height. Now, again, we want to optimize the surface area given what we know about the constraint, and we also have another thing in this question where it says the diameter of the can must be no less than 4 and no greater than 8. So the domain here, we have 4 is less than 2r, which is less than 8. So in other words, 2 is less than r is less than 4, right? You can't have a radius bigger than 4 if you can't have a diameter bigger than 8. Okay, so there's our domain. So what we're interested in here is we want to look at that surface area equation. It's 2 pi r squared plus 2 pi r h. But of course we can't optimize it right now because it's not a function in one variable. So let's add a sort of mini step here. Isolate a variable in the constraint equation. So I'm going to isolate h. I'm going to say 250 equals pi r squared h, right? Pi r squared h. Okay, because we know that 250 is the volume, and the volume is pi r squared h, which means h is equal to 250 over pi r squared. I'm just going to copy pi so it's on my clipboard. Okay, and that's we now have this, okay, which is what's going to enable us to go back to the original equation and replace h. So we're going to go create the equation of the optimized quantity with one variable only. So here we go. Surface area in terms of the radius is 2 pi r squared plus 2 pi r, and then instead of h, I'm going to write 250 over pi r squared. Okay, and you see what I've got here? I've now got an equation that does everything I need in terms of only one variable r. Remember, pi is not a variable, pi is just a constant. So let's clean this up a little bit before we do our calculus. So surface area radius is equal to 2 pi r squared. You definitely want to simplify before you go further, right? Now, look at the other equation. We've got 2 times 250 on the top, 500. Then we've got pi on the top, pi on the bottom. They cancel. We've got r on the top and r squared on the bottom. So we're left with 500 over r. Okay? Now this you can take the derivative of. We could just write it one last way here. It's 2 pi r squared plus 500 r to the power of negative 1. Right? The negative 1 makes it a little easier to differentiate. Surface area in terms of surface area prime, okay, is going to be 4 pi r minus 500 over r squared. Right? And that's going to be our equation that we need to optimize. We know that the best possible answers here, the best possible answers are, sorry, just create this again. The best possible answers are surface area of 2 or surface area of 4 or surface area of any critical point, right? We know that the best possible can has to be one of those things. So we could check. Let's find the critical points first, and then we can come back. We can loop back around to this. So surface area. Let's set the surface area equation prime equal to 0. Sorry, why this is doing this to me. Okay. Surface area prime equals 0 to find the critical point. Therefore, 4 pi r minus 500 over r squared equals 0. Okay? Now, we know that r cannot be 0 here, or we would have undefined, but keep in mind that r has to be between 0 and 2 anyway. So what I'm going to do is I'm going to multiply through by r squared. Okay? And what that's going to do is it's going to just simplify things a little bit. So I get 4 pi r cubed minus 500 equals 0, right? I could divide by 4, and I get pi r cubed. What's 500 divided by 4? 125 is 0. Okay, and therefore you get this answer, which is that r cubed is equal to 125 over pi, and that therefore r is equal to, plus or minus, no, sorry, not just, sorry, just minus 5 over the cube root of pi. Cube root pi. Wait a second. There we go. Okay, so the radius, so the ideal radius here is 5 over the cube root of pi. So now what we need to do to find the absolute min, we need to compare surface area of 2, which is the left end point of our area, surface area of 4, and surface area of 5 over, pi, cube root pi, this number. Let's copy paste it and type it out again. Okay, so those are the three values that we need to check. Let's go back up to our surface area equation. It was here, right? So this is the equation that we need to sub into. So you got to sub in 2, 4, and 5 over cube root pi into those into that equation. Let's try that. So let's go back and make a new equation. Okay, so we're going to start with r is just going to be x. The height we said was 250 divided by pi r squared. And then we said the surface area was 2 pi r squared plus 2 pi r h. Okay, oops. It thinks that's one variable. Okay, so there's our surface area equation again. If we simplify, okay, we get that. So this is again in terms of r. I used x instead of r. So if you look at the surface area graph, so again, let's get rid of the height and radius. Oh, I'm sorry. I was like, this doesn't have a min or max. Something's definitely wrong here. Sorry. This should be in the bracket on the bottom. There we go. Okay, so the surface area, we have two candidates. So we have surface area of 2, surface area of 4, and surface area of, we said, 5 over the cube root of pi. So pi to the power of 1/3. Okay, so the three options are, right, so SA 2 was 275.13, SA of 4 was 225.53, SA of our critical point, just rather than write it out again, is 219.66. So the least possible material used is 219.66. Okay, or 69, sorry. 69. Okay, and that's the best possible can that you can make. Now we were asked to find the dimensions again, so make sure we actually do that. The dimensions. Okay, the radius is 5 divided by pi. Sorry, so that's just what is 5 over cube root pi. 5 over pi to the power of 1/3 is 3.41. So 3.41 is the correct radius. The correct height, remember, was just given by, let's go back to our equation for the height, was 250 over pi r squared. So 250 divided by pi times 3.41 squared. Now again, you really shouldn't be using 3.41. You should be using more decimals than that. So because we don't want to, we don't want to make a rounding error. So 41392. We'll do that. 4.3192. Okay, and the height that you get when you sub that in. So let's do that quickly. To 250 divided by pi divided by d squared. We get 6.82, 78 whatever. So again we can 6.82 784. So then what we could say is the ideal can has a radius of approximately 3.41 and a height of approximately 6.82. Now there's an important lesson actually in this, which is that the idealized can has a height of double its radius. For a thinking question, prove why. Would be an interesting thinking question to try. Okay, so here's how you do it with a cylinder. Again, make sure with a cylinder you refresh on the equations for the surface area. I want you to visualize this. Why does the surface area have this equation? Why does a volume have this equation? And then you go through and use our regular optimizing algorithms. Again, from the picture here, you can see that when I draw D and SA of D, I get that perfect point there at the absolute minimum of the interval. Remember, for this one, we're really only drawing the function between 2 and 4. So, actually don't need this or this. Sorry, this. We're only looking at this little interval, so we checked it at 2, we checked it at 4, and we checked it at 3.41, and 3.41 was the ideal spot.